Thank you, Chairman, for the introduction. The presentation consists of three parts. The first part is about the motivation of this research, that is to achieve even higher IIS computation accuracy. The second part is about the rationale of range effect. Finally, we will present a straightforward strategy to counter range effect and use it for attitude reconstruction. We know that, in principle, IS integrates gyroscope and accelerometer measurements to produce attitude, velocity, and position. This slide lists the strap-down inertial navigation equations. The talk is related to how to solve them in a highly accurate method. In recent 5 years, my group has proposed a functional iteration method to solve the above inertial navigation equations. The intermediate researches were ever consecutively reported in this symposium in 2017 to 2019. On the right side is a flowchart of the established algorithm and a filter. Notably, the algorithm feeds on the fitted angular velocity and specific force polynomials. With the fitted angular velocity polynomial, the attitude is iteratively computed. Then, with the resultant attitude quaterning and the fitted specific force polynomial, the velocity and the position can be iteratively calculated. The algorithm can bring the IS computation error down to the machine precision. But of course, it depends on the quality of the fitted polynomials from sensor outputs. Last year, I collaborated a paperwork with Dr. Yuri Litvinovich on comparing the functional iteration approach with the traditional Taylor series expansion approach. This slide shows that under relative Koenig frequency of 0.01, machine precision attitude computation can be achieved by both approaches. The attitude error quickly goes up along with the increased motion dynamics. The Taylor expansion method numerically fails when the relative Koenig frequency approaches 0.1. We were sure under dynamic motion scenarios, it is the so-called range effect that hinders further accuracy improvement. Interpolation and range effect. Here is a demo of range effect. With small sample nodes from 8 to 16 and 20, the interpolation quality in the middle part becomes better, but that of the boundaries worsens with large error spikes on both sides. In fact, the range effect is quite common, more severe in high-order interpolations on equispaced nodes. On first thought, there seems to be a contradiction, because polynomial interpolants are supposed to approximate smooth functions as closely as possible if the number of samples are sufficiently large. Is it right? In fact, the close approximation of polynomials to a smooth function is preconditioned on the distribution of samples. The so-called Chebyshev points are among the best hands-on nodes that is not only free of range effect, but supports quick convergence. Chebyshev points defined to be equispaced on a unit circle turn to cluster together on both boundaries of the time interval. Unfortunately, all IS systems have time equispaced outputs, and the equispaced nodes are among those that are exponentially ill-conditioned in terms of numerical stability. For signal values f sampled at time nodes t, the common linear interpolants, such as the Lagrange interpolants, can be expressed in a well-known barycentric form. Different kinds of nodes will have different widths, as will be shown in next slide. The interpolation error is affected by two factors. The first one is related to convergence property of the interpolant, and the second one is characterized by the so-called Lebesgue constant. By definition, we say that the Lebesgue constant is uniquely determined by the interpolant itself, namely the width and the nodes. The Lebesgue constant participates as a multiplying amplifier of the signal errors. Computer rounding or signal sampling errors might be considerably amplified or even cause divergence in practice, depending on the distribution of the nodes. As mentioned above, in the barycentric form of interpolant, different kinds of nodes correspond to different widths. This slide lists three kinds of interpolations we are concerned with. The first one is polynomial interpolations on equispaced nodes. The second one is also polynomial interpolation, but on Chebyshev nodes. The last one is the so-called EFH rational interpolation on equispaced nodes. Notably, the EFH rational interpolation was a significant advance in the numerical analysis field for the last decade. Here lists the theoretical bounds of Lebesgue constant for the three kinds of interpolants. Along with the increased number of nodes, the polynomial interpolation on equispaced nodes has a fast increasing lower bound of the Lebesgue constant, while the upper bound of Lebesgue constant for EFH rational interpolation is much smaller. Judging from the established results, the EFH rational interpolation is supposed to deliver a much better result. This is an interpolation example of sine function for 20 nodes. The sine function is sampled at 100 Hz, and thus an interpolation window has a duration of 0.2 seconds. The bottom row presents the Lebesgue constants, and the middle row plots the interpolation error. It appears that the polynomial interpolation in red has much larger Lebesgue constant and the interpolation errors as well, especially on the boundary of each interpolation window here. In contrast, the EFH rational interpolation in blue performs much better. You may have noticed there are extra results in black. They are for special BAC borrowing and cutting policy that uses neighboring nodes beyond interval boundary for interpolating, but only keeps the interpolant segment on the original interval, in view of the fact that the round effect has relatively little influence on the middle part. Next, the interpolation methods are applied to gyroscope measurements for attitude recovery. Gyros usually have two output forms, angular velocity and angular increment. We take the angular increment as an example. In the polynomial BAC strategy, when interpolation is performed on the current time interval, the gyroscopes from previous and later intervals are borrowed to participate the interpolation, but only the fitted angular increment polynomial on the original time interval is used for subsequent processing, namely by time derivative to obtain the angular velocity polynomial. Then the angular velocity polynomial is used as input for attitude computation by functional iteration. The classical conic motion is used to assess the attitude accuracy of different interpolation methods. This figure plots the principal angle error as a function of relative conic motion, coding frequency. That is the ratio of coding frequency relative to signal sampling frequency. The advantage of EFH rational and polynomial BAC interpolations is prominent, and notably, the polynomial BAC interpolation gains about 5 orders of magnitude in accuracy, as compared with the normal polynomial interpolation. Specifically, the attitude error of the polynomial interpolation in blue begins to quickly rise from 10 Hz onwards, while that of the polynomial BAC interpolation in black does not significantly increase until 100 Hz and after. Moreover, as indicated by the dashed black curve, when the number of samples in the interpolation window is increased from 8 to 16, the benefit of the polynomial BAC interpolation is further enlarged. These plots are the results for error-contaminated gyro outputs. The first case simulates high vibration environment in the left figure, and the second case mimics highly dynamic motions like those experienced by smart munitions in the right figure. The error behaviors are quite similar in both cases. For coding frequencies below 60 Hz, the gyroscope measurement error dominates the attitude computation accuracy, and the attitude errors are flat lines for all interpolations. The normal polynomial and EFH rational interpolations began to rise at 60 Hz and 150 Hz, respectively, where the computation errors start to take the lead. Notably, the polynomial BAC interpolation just keeps flat in the whole range of considered coding frequencies. Summary: high-order polynomial interpolation is prone to range effect on equi-spaced samples. The borrowing and cutting strategy is very effective in depressing range effect, that is, unexpectedly outperforming state-of-the-art EFH rational interpolation. Polynomial BAC interpolation much enhances attitude accuracy for highly dynamic motions, which is potentially extended to the whole inertial navigation computation. Thank you for your attention, and I'm happy to take questions.